I want to draw shear diagram for this configuration. One meter, 1 meter, 1 meter. Now, question here is, I want to draw shear diagram for that. What should I do? Yeah, so basically, the first thing you do is say, well, you find the external reaction. In fact, just draw free body diagram. So that's your beam. You have a vertical reaction. Let's say this point is A, this point is B. So you have AY, and then BX, BY. And then here, because, this is an important point, because this is the external load on your system, you're not cutting it, this is from here, then you can safely replace that with a single load or point load at the cross-sectional area or centroid, right? Because this is external. But when we cut it, you cannot first replace that with a point load and then cut it from here and here. You should consider distributed load. Cut it, when you cut it, then it becomes the external load of your chosen system. Then you can replace it with point load. That was the point. So here, if this is 1, this is 1.5, and then the location is 1/3 from the left. That's your FPD. Now, I want to solve for this guy. If I want to draw my shear diagram, which way you want to go? Let's say I want to go from left to right. So probably what I would need is only AY. And a part of like AY from here to here, and then after that, a part of that. I don't really need to solve for BX, BY. So for that reason, all right, summation of moment must be 0 to find AY. So you don't really waste your time to find BX, BY, because you do everything from left. This may change in other problems. So your strategy, you got to make some sort of a strategy like that before actually you start solving, because you won't have enough time, especially in the exam. So if I solve that, I get nothing from these two, then 1.5, and this also K. 1.5 K times 1/3 multitude, and then you go negative AY times 2 is equal to 0. Then you solve for AY. AY is equal to
0.25.
0.25. 25. Thank you. So here, I just simply, instead of that, I just put 0.25 K, if that computation is right. Now trust. Now, I really don't need this, so I safely erase it. That computation was only to find AY. Now I want to draw shear from here all the way from left to the right. How many different intervals should I consider? 3. From here to here, And then from here, you have something that changed the scenario. So you have to compute from here to here separately. And then from here to here, you have some sort of visible load. And then from here to here. So first, let's take my x from left, and let's cut it somewhere here, between 0 and 1. Right? So that's your x. And you're cutting it between 0 and 1. So you have something like that. This is the beginning, and that's the point. So what is its length? From here to here? X. Then at this point, you're going to have the shear load and a bending moment, an axial load. What else do I have in FED? Nothing. That's all I have. So what can you say about these three components? They are 0, right? So V from here to here is 0. So I simply say raise it. If I want to draw that, my shear diagram, that's my x, and this vertical axis is shear in kilonewton. So from here to here is simply 0. There you go. Zero. Now I go from point x between 1 and 2. Okay? What should I do? Again, make your FED. Big system right now, you see you're scrolling this card to right here. So you have a new card, new system, so you have to draw your new FED. So I draw it here. This is AY, which is 0.25K. And from here to here is x, again n, v, and m. And that's all. That's all I have. So what should I write for that system in order to get v directly? Summation of force in y, one equation. Right? If you do that, then you get v is equal to positive 0.25K. And look, the sign is important. You'll see that. So don't say, well, I have 0.25K. I don't know if it's positive or negative. Well, if you write summation of force in y, then you get 0.25K positive, negative, v is equal to 0. So v is positive 0.25K. So I have something from here to here all the way. You have a positive 0.25K. Right? Now I finally go to this section. So I increase this x. I screw it all the way right to somewhere right here. See that? And this is between x is equal to between 2 and 3 in this interval. So that's your x right now. So what should I do? The same thing I did to start over. Later in the structural analysis, next course, we teach you a method so that you do it in one shot. You don't need to do it 3 times. You just do one shot, and you write this relation in just one line instead of 3 different relations. Right? So this is your cut. This is your, you already have 0.25K, and from here to here You have a part of this distributed load, not all of it, just a part of it. So let's say this part is H. From here to here is what? From here to here, is what it is? X. What else we have here? M. Good, M positive. B. M. Right? And this is well, and that's all. What else do I need to find? The amount of, say, which one? You see, the amount of force is known here. The amount of triangular that is involved in our cut. So that part is in fact right here. We're talking about this force, right? The force comes from that little triangle. So how can I find that? Well, just try it here. This is the big triangle, and this is the small one. So the big triangle from here to here is how much? H. From here to here, H. We don't know. From here to here is 1. From here to here is what?
X minus 3.
X minus 2. That's an important point. You see, from here to here is X. From here to here is 2. So it's X minus 2. You see that? So the relation that I write between these triangles, the shaded one and the bigger one, is 3K over H is equal to 1 over X minus 2. That means H is equal to 3K X minus 2. Right? So here, my H, let's write it here. Now I found my H. From here to here is 3K times X minus 2. Now I go ahead and right now I can safely replace this distributed load with the point load. Because what? Because for this system, now this distributed load is external load. You're not cutting it anymore. It's just simply external load. Now if you were supposed to cut it again, you cannot say, well, first let's replace it with point load, and then I can cut it here, and then I have no load. When you can, when your distributed load is external, your system, then you can replace it with point load. For that system, this is external load, right? So I can replace it with point load. And what's the value of the point load? First, I know that this is going to be replaced at the center, like that. What's the value of the distributed load? Say that?
1.5 x minus 2 squared.
Why x minus 2 squared?
When you base it, x minus 2, so you can put 1 half base on top.
In fact, if you explain it, you're just making the final answer. You explain it for the rest of the class. When you say the area of that is equal to 1 over 2 base times height for this triangle, right? And what is base? You come here, you say x minus 2. So here, you say 1.2, 1 over 2, x minus 2 times the height, 3k x minus 2. Now you go finally to the x minus 2 squared, so you get 1.2 times 3k, 1.5k times this combined with this. Now that was the step that was mentioned. X minus 2 squared. Now when you say that from the beginning, you say x minus 2 squared. Well, how did you get that squared? We had a student in a structural analysis class. Seriously, continuing movies. How do you get that squared? say, well, you were supposed to have this in consolidated class. So this simply, this is not a magic that you say. This comes from the area of this part of triangle. Right? So let's put it here. The shear load becomes 1.5 A x minus 2 squared. And where is the location? The location is from here to here. Again, when you say the answer, you need to explain it. You say 1/3 of the base. 1/3 of from here to here. But what is from here to here? Then you come here, you see, x minus 2. It's not 1. Again, we have the student say 1/3 of 1. Put it there. It's 1/3 of, let's write it here, 1/3 x minus 2. Okay? Now you're simply ready to write the equations. So I want to get my v. What should I do? You see, I'm not interested to find bending moment. Neither am I interested to find the n, actual load. What do I need to do? Summation of forces in a y direction. So you say sum f in y 0. So you say, starting from this, 0.25k, positive, negative p, then negative the amount of this force, which is 1.5k times x minus 2 squared. Do I have other vertical loads? That's pretty much all. Then you solve for v. Then v is equal to this is equal to 0. Then solve for v. Then you get v is equal to 0.25k, right? Minus 1.5k x minus 2 squared. That's your shear relation. Now I want to plot it. What kind of curve is that? It's a parabolic curve. First of all, how many of you guys got this right, correctly? So there was a meter waiver. None of you? I think I saw a parabolic curve. I don't know who was that. You did, Tom? No?
I think I did, but I didn't write out the equations.
I think I saw a parabolic curve. So what happens here, for this parabolic curve, how many points you need to draw it? If it was a constant value, how many points you want to compute in order to draw it? If it was just a constant value? Just one point. Right? Because if you know 1 point, you just put the constant at that point. If that was a line, how many points? Two. Beginning, end. Now, if this is second order, it's like 1 plus line, then how many points do you want to plot? 3. Right? Or 2 point and a sign of convexity, upward or downward. Right? So, my 2 point, 1 would be here, 0.2. Because x is from here, right? 0 is here. Put 2 in the x. What do we get? 0.25. So the first point is right here. Now put the second point I'll choose is the next, the last one. So x3. Put x3. What do we get? I know that we do a budget structure with negative 1.25. So if that's it, we get somewhere here. Negative 125. Okay. And then you want the convexity. What's the curvature of this parabolic, is it upward or downward? You see the coefficient of x squared, you look at the coefficient of x squared, what's the coefficient of x squared? It's a negative number. The positive is convexity is up. Negative is like that, right? So you have some sort of change, probably like that. Right? Now, if I ask you, let's go back to this problem. If I ask you, because your ultimate job is design engineer, right? If I ask you, design that beam for maximum shear, and when you want to apply the safety factor and load the stress, this should happen the point that your shear is maximum. Here, everywhere shear force was 4K, everywhere. Now, what point do you choose there in this case in order to apply the safety factor to again? Huh? Yeah, look at here. The absolute value of the magnitude of shear. Right here. Here, also you have to check. Maybe this has this has an overshoot like that. And maybe this by itself is greater than the magnitude of this 1.25K. So you have to find the maximum here, right? And put the value here, see what maximum is positive. Or maybe it's simply straightly go down like that. So you have to, what's the conclusion? You have to have some sort of plot. That's the reason we draw as an engineer. The most important thing in sports is shear moment diagram. Let me make it short. In this course, if you learn how to draw shear moment diagram, you are eligible to pass this course. But if you cannot draw shear moment diagram, you won't pass this course. You will not pass this course. I'll guarantee that you will not pass this course. So the thing is, this topic of shear moment diagram is next chapter. It's not right now. But I'm just walking you guys through it, give you some introduction. So when we reach to the actual shear moment diagram, then you pretty much know everything. Right? So put a lot of time on drawing these diagrams and understanding it. Because this is very important. When you look at this curve, you just immediately say, my design point is here. It's a maximum shear. Right? And you need to have this sort of diagram for your actual structure. Later on, you will see there is a software that generates this for you, for your actual complicated structure. But you have to be able to interpret it, to read it. When are you able to interpret it? When you actually can draw it yourself. At least basic ones. Yeah.
So to test if the point just, or if the slope just goes down, or if there's a maximum between 2 and 3, would you just plug in like 2.5 or like 2.6?
I would find the maximum. How do you find the maximum of that? Then take a derivative, then make it 0.
Yeah.
And then you find the x of maximum, and then put x of maximum here to see how much shear you get. So I wouldn't say just take the between and put it here, because the maximum may not happen exactly in between. I would actually draw it. That's the reason they ask you to draw shear moment diagram. Because if you draw it, it's just a solid proof that you can see it just immediately from the curve, where the maximum happens. And in fact, when we're talking about shear moment diagram, we're talking about one single maximum. So it doesn't matter how complicated the curve is. We're talking about single maximum or sometimes minimum, right? So now let's go to another example. Now I want to talk about the strain. I want to talk about another important thing. So far we talked about the stress. And now we talk about strain. Strain. Therefore, is non-dimensional quantity. Therefore, is a non-dimensional quantity. So far we talked about the stress in the previous lecture. Stress was related to force per area, right? So if you know that well, if you have something like a bar and you have some sort of force, then you have axial or normal stress, right? So we talked about that, we computed it, we draw a diagram for that. Now another important thing is the deformation. So the deformation, you know that if you apply that force, your bar is going to stretch a little bit, like that, and you have some sort of, let's say, delta deformation. In fact, it acts like a spring. Most of you guys already have mechanical material, and we're talking about spring constant and Hooke's law. Now, I want to bring everything in the same context. So, this deformation, you know that if you release this force, if this force is not too big, if you release it, what happens? It goes back. This ball is going to go back, not exactly this spring. So it turns out that in mechanical material, the scientists realized that there is a relation between the amount of force and consequently the stress. There is a relation between the stress and this deformation. And in order to quantify that relationship, you need to define another parameter. So far, we didn't like force. We defined the stress. We divided by area and became the stress. We could use force, but the stress is more scientific because it shows up in the actual equation that we designed. Another parameter is we don't want to use this actual deformation. We want to make it something like divided by something. That's the reason we introduced the strain. The strain is, in fact, the concept of deformation, but it's kind of relative. So you say the strain is equal to delta over L0. Right? So, in fact, this actual deformation that you compute, deformation, not the total length. If you get total length, let's say total length minus L0 initial length. The actual deformation divided by L0. What's L0? The length of this go higher. L0 is from here to here. How about this one? This is the right. So the amount of deformation, don't forget, I'm not saying the total length. The deformation, that means total length minus L0. Let's write it here. L mu minus L0 divided by initial length. L0. This quantity, they call this a strain. And then they have a nice symbol for that. In fact, you have a Greek letter for stress. Now you have another Greek letter for this epsilon. So this is in fact some sort of displacement. But what's the unit of that? It's a unitless. Why? Because I'm dividing length by length. Right? Example. Let's say you have the same problem. Let's say this deforms by 2 millimeter and the initial length is 3 meter. That's too much deformation. Usually this value is in order of 10 to the negative 6 in actual practical application. Like this structure, this building, I mean, when I walk, you may not believe it, from one side of the room to the other one. If you plot the deformation of these beams in this structure, they have deformation, time-dependent deformation. But it's order of 10 to negative 6. That's the reason you don't see it. 10 to negative 6. They actually deform. It's just crazy, you know. If you can magnify it, if you can, you know, get this data and in computer multiply it by 10 to 6, 1 million, then you see this beam actually is going to deform like that. You can see. So this is a lot of information, 2 millimeters. So the question is find sigma. Find epsilon, find strength. Well, like you quiz, again, this is very simple. We just use the definition. Epsilon or the strain is equal to delta plus 1 delta 2 to negative 3 divided by the initial length, which is 3. So you get 2/3 of 10 to negative 3. There is no unit for that. Don't write millimeter. There is no unit. Right? So another thing you could say, well, I can use millimeter because millimeter divided by millimeter is one-dimensional. So you could say instead of that, you could say 2 millimeter divided by 3 meter, and 3 is 10 to 3 millimeter. Millimeter cancel out. Again, you have the same thing. 2/3 of 10. Whatever you like, do that. But make sure that they are consistent, because they should cancel out. Now, I want to go over, because we're going to have next class, I'm going to give more examples in your book about the strain computation. But I want to just close this topic, the relation between the stress and the strain. Just very quickly, I want to put everything together so you see the big picture. And then next class, I want to do more examples from both. Now this topic is the stress, the strain relation. Intro to Hooke ultra in elasticity. So they actually realized, scientists, and I'm talking about like 200 years ago. This is a very well established science, very old, but still they are doing research in this area. So they realized if you have a specimen like that, right, and apply a force to one energy and compute the value of the stress here in the middle. What's the value of the stress? The stress, let's put it here, is equal to force divided by area. And I'm talking about right now, we're talking about the axial or normal stress. That's the reason I use sigma, I don't use tau. But the same concept can be applied for shear too. The same concept. I mean, if you apply shear load and then compute the shear strain, we talk about that later. Right now, everything is normal. Right? Everything is axial. They realized if they plot sigma at the middle of it versus epsilon. So what's epsilon? The deformation of that divided by initial length. They realize if they go to the lab, put this in a machine, compute the stress here, how do they measure the stress? They use a stress gauge, right? And then how do they measure the deformation based on the strain, right? The change in the length divided by L0. They realize if they plot that, the moment you, first of all, if you don't have force, what do you get for a stress? 0 force, 0 deformation. Then when you increase the force, this will go up like a linear fashion, like that, to some extent. And you can expect it because this is going to act like a spring. If the force is small, if you release, it's going to exactly come back like a spring. And then at some point, it's going to have a little bit change in the behavior like that. And then it's going to behave like this way. This region, we call it, so in fact, let's use points right now. So we have a point here, some points here, and then when you apply too much load, then this is going to go down, and this is going to break. So in the actual mathematical world, we're talking about something that you can extend it forever. But I say, if the load is like 2 giganewton, compute the stress for the specimen of length of like 1 meter, like this. And then you put in a calculator, and then a strain deformation is, not a strain, the deformation is like 200 meters. And then I say, well, did you use chewing gum? And it's just math. But that's not correct. In the actual world, you see, you can go to some extent within the linear region. And then after that, it acts like a plastic material. With the almost constant force, you don't need to apply more force. You just keep that force and it's going to extend. See, too much extension. Just keep the same force, it's going to extend. It's like chewing gum, plastic. And then at some point, it's going to break. It's going to break, right? So this curve, they get it from lab. Get it from lab. So you get this curve from lab. So look, you're not interested in this region. Now this good thing about this course is, where do I put my black marker? Really do need a black marker. Oh, that's a blue one. So here, we're not interested in this course, in this area. This called elastoplastic region, or highly nonlinear region. This region is for researchers, scientists, graduate students who wants to develop papers. In engineering, we say we don't want to go to this region. But in this region is that you have permanent deformation, material failure, crystal structure change. So you don't want to go to this region. We are working in this region. Now, what is that region? It's a linear region. That region is called elastic region. What can you do about this region? Well, you can simply treat a line, right, in these points. A regression line. So if you fit a line, what can I write about the equation of this? You can say sigma is equal to the constant times epsilon. Look, I'm just writing a equation of line in the sigma epsilon axis. Sigma is equal to something times epsilon. And what is the initial deflection? 0. So you have exact sigma is equal to something times epsilon. What is that something? Well, I want to reach to that. That constant is what in this curve? We will reach to that. Just look at this curve, this line. What is that constant? The slope. You see, this is, let's say, y versus x. You have a line. Then you say sigma y is equal to something times x. What is that something? The slope of this curve. Look, the slope. That when you go to lab, and do this experiment, you can simply find this slope from the lab data. They call this a slope Young's module of elasticity. And this comes from lab. You don't compute module of elasticity, it just comes from lab. You have to take your specimen. Now, this is different for every single material, aluminum, steel, you know, you have to make your specimen like that, go to the lab, put it in a machine, apply the stress, and measure the strain, and draw this curve. The shape of this curve is same, the behavior, but the slope is different for different material. That's the reason they say Young module is different. And the character they use for that, or the symbol, is E. Capital E. So in this course, let's talk about some nomenclature definition. E capital E is Young module. Now, if we do the same thing, we'll talk about that later. But for shear stress, that means if you put a bar like that in a machine and apply torsion to that, again, you have the same, if you measure torsion versus shear deflection, or angular, this is angular deflection, then you cannot go forever like that. You cannot twist it forever, right? Your reaction torque will increase like linear and then go some flat and then break, torsional break. So you have the same thing, but the slope there, they call it shear module of elasticity. You see, this is the Young module of elasticity, or normal stress module of elasticity. In that case, we have shear module of elasticity. We show it with G. We'll talk about that later. But E is the most important one right there. So, in fact, the final equation is sigma is equal to E epsilon. So we will see what kind of use we use. That equation is like a miracle. You remember I talked about indeterminate system. With that equation, you can solve it. You can make everything determinate. Example. Let's say, I don't want to actually solve it right now, but I just want to give you some exposure to this concept of indeterminate system. Let's say you have a bar fixed to the bar, and then you have a 2K here. And say the reactions here is A, point A, and B. Now the question is find the reactions at point A and B. Can you do that? Why not?
Because the moment would be useless and you don't have anything in the line, so you only have one equation.
And how many unknowns? And in fact, math is one of those final midterm waiver bonus hunters, heavyweights who got a waiver. Was it final or midterm?
It was midterm.
Midterm, yeah. Sometimes he does very outstanding solution in class. I really get something very impressive. But that problem, if you go ahead and draw FED, what do you get? Well, for that, at point A, you have AX, AY, MA, and at point B again, DX, DY, ME. Now, you know what, you don't have anything in the Y, and you don't have any sort of moment generator, right? So let's get rid of these moments, even though the actual problem is more complicated than that. But because I don't have anything in the Y or any moment, I'll just say the minimum is actually AX and EX. Now, how many equations do we have? I already applied my AY equation, summation of force in Y. I already applied the moment, wherever you moment equation right is a null equation, 0 is equal to 0. So how many equations do we have? One equation, summation of force in X, 0. Or AX plus BX is equal to 0. Sorry, plus 2K. Plus 2K. There is a 2K also here. Don't forget when you write. Is equal to 0. Now, the question is, what is the value of AX and EX? You can't say, well, you know what, this is indeterminate. Is this really indeterminate? If you go to the lab, you're just in a machine and apply this load and put some sensor. Sensor here, sensor here. And then you look at the computer. The sensor says indeterminate. The sensor gives you some value of force. So the question is, if I only have one equation, then how can I find this guy and this guy?
You could write a function that would give you an estimate for both of them if you have the other one.
Huh?
You write a function, then if you have one of them, you can find the other one.
I write the function.
I mean, you could just set it up kind of like how it is right now, where you need one of them to find the other one.
I need one more equation, right? That's what you're trying. That's right. I need one more equation. You see, how many unknowns do I have? 2. How many equations do I have? 1. I need one more equation. And that one more equation, you haven't had it so far in vector statics. That comes from this. It's a magic. So what can I write about deformation of the total bar from here to here? The relative deformation B with respect to A is what? These two bars are fixed. Is 0. So with that said, you can apply this equation. So you find a relation between that 0 and the sigma. And sigma is what? Sigma is not 0. If you put a sensor in here, it's going to show you the stress. Sigma will depend on the axial load. And the axial load depends on AX. If you draw, that's the reason I say we have to practice the shear moment and axial load diagram before actually you go to solve a problem like that. In your board, he puts all this topic at the very end of the board. It's just opposite. But here you have to first draw your axial load. If you draw your axial load, how much is axial load here, from here to here? Negative AX, right? And then you go from here to here, is AX, negative AX plus 2K, right? So everything, the axial load depends on AX and dx. So the stress is therefore depending on AX, dx. And the epsilon, total epsilon 0. So you find another equation versus AX and dx. Then you have two equations, two unknown, then you can solve it, make it determinate. So why do we study Hooke's law? The most important application of that is in solving indeterminate problem. And I'm telling you, 99.99% of engineering problems are indeterminate. You make it determinate, you simplify it. But in the actual life, they are indeterminate. So you have to utilize this knowledge. Mechanics, in fact, mechanics of material is more practical than the actual electrostatics. It will give you more precise. And also that depends also on what? That depends on type of material. So you have to check if your force is small enough, so you are on the elastic, you will not here. You can predict the failure. So next class, we are going to solve more examples about what we said we are going to solve more examples for strain and more examples for stress.